Okay, we have notes, chapter P, section 6 continued, more rational expressions. Here we're going to see and learn about how to add and subtract rational expressions with the same denominator. Okay, so this is when the denominators are the same already. This is what you're going to do. First, you're going to add or subtract the numerators. You then place the result over the one common denominator. Simplify if it's possible, and don't forget about listing your domain restrictions. Remember, the restrictions are what x is not allowed to be, whereas your domain itself is the values that x is allowed to be. So your restrictions is what it can't be. So the first example that we have here in this part of the notes is add or subtract. Two fractions. Notice the denominators are the same already. So we've got x divided by x plus 1, and this is a quantity. And we're going to subtract from it quantity 3x plus 2 divided by quantity x plus 1. Now I'm putting parentheses around that because you have to start looking at them as quantities. They're not always going to be typed out for you that way with the parentheses. But they really are quantities signifying one number. All right, the denominators are the same already. So what we're going to do is we're going to write one fraction bar with that one common denominator, which again happens to be a quantity. And we're going to write this x subtract the quantity. You must write it here as x subtract the quantity because you need to distribute the negative sign to both the 3x and the 2. Okay, moving right along. We're going to do exactly that. This becomes x subtract 3x subtract 2, all divided by the one common denominator, x plus 1. We do have like terms to combine, so let's combine those like terms. We've got two linear terms here. X subtract 3x is negative 2x. Subtract 2. All over x plus 1. Notice in the numerator, you do have a common factor with those two terms in the numerator. So we're going to factor out a negative 2. Remember, we said whenever there's a leading negative, we're going to take that out. So negative 2 multiplied with the quantity x plus 1, all divided by x plus 1, which also is a quantity. And that simplify if possible part, well, it is possible because I have a common pair of binomials that I can divide out, one in the numerator, one in the denominator. My final answer here, simplified, is this expression will always equal negative 2, no matter what the value of x is, except when x is negative 1, right? Negative 1 would provide a 0 in the denominator, so x is not allowed to equal negative 1. Final answer, simplified form. I have subtracted these two fractions and found that for every value of the variable x, I'm going to get a negative 2, except when x is negative 1. That is subtraction when the denominators are the same already. The next example in our notes here, again, the denominators are still the same. So the process is still the same. Remember, think of these as quantities. You cannot divide out terms, okay? So don't try to be dividing out those 3x's. That's not a thing. We're going to put this over the one common denominator, 3x plus 4. And again, it's a quantity. And we're just going to copy what's here. This binomial plus that binomial. And I do like to put parentheses around them. I know it's really not that necessary to put them around them for this problem because of the addition. I'd really be distributing a positive 1. But it is important that you put the parentheses when you're doing a problem like this one, example 5a, because we did have to distribute a negative there. So I think if you do the same thing each time, you're less likely to forget when you need to put the parentheses if you just write the parentheses all the time. All right, so since I am just distributing a positive 1 there, I could just simply, combine this. This is 3x, add 2, add 3x, add 6. So 3x and 3x is 6x. 2 and 6 is 8. Notice both the 6 and the 8 are even, so it's divisible by minimum a value of 2. So I'm going to factor a 2 out as a GCF. Factor means divide, so I'm dividing both of those by 2. I get 3x plus 4 as a quantity, and look at that, 3x plus 4 quantity in the denominator. I have a numerator-denominator pair that I could divide out, and so simplified version of this, the addition of those fractions would always equal positive 2, if and only if x is not one particular value. So I do have to list the restriction. Remember, the restriction is part of the answer. You can't skip it. All right, how do I figure it out? Well, remember, the denominator can't be 0. Okay, and a quick, easy way to figure this out is all you have to do is change the sign of the constant and then divide by what's in front of your variable. Right? If you recall from zero product principle, when we were solving equations, we said 3x plus 4, you can't equal 0. You would subtract the 4 over, so 3x can't equal negative 4. And divide by 3, x cannot equal negative 4 over 3. But we could get that quickly if you just visually look at this and say, oh, change the sign of the 4 and then divide by the 3. Same thing up here with this example. If I change the sign of the positive 1 to negative 1 and divide by what's in front of x, which happens to be a 1, negative 1 divided by 1 is still negative 1. There's my restriction. Okay, so this was just, how to get that restriction value quicker when you had a binomial in the denominator. And let's look at x is not allowed to equal 4 over 3. Final answer. Now we're going to move on to adding and subtracting rational expressions with different denominators. Okay, so what happens with this is when you're adding and subtracting rational expressions with different denominators, you must first make the denominators be the same by finding the least common denominator, or the LCD. Again, these are different denominators. You must write the product of the distinct factors, and we're going to talk about that and how to build an LCD. So my first example here, it asks me to add or subtract, and notice that the denominators here are in fact different. X plus 1 in the first denominator is not the same as x subtract 1. They are different denominators. So I cannot say that this is 3 plus 5 over x plus 1, nor could I say it's 3 plus 5 over x minus 1. It's kind of sort of like, and I'm going to go off on a little tangent over here on my paper. Suppose I had two fractions, like 2/3, and I wanted to add 1/5. I can't just add numerators and denominators. This thing does not equal 3/8. I would have to get a common denominator. So the only value that I can make both of these denominators be to be the same as 15. Agree? So if I make this 3 become a 15, and this 5 become a 15, I can only achieve that by multiplying by some number. Well, 3 times 5 is 15, so I'd have to multiply the 2 by the 5 to make that 10/15. Right? If I would simplify 10/15, I would get 2/3. And here, if I would simplify 3/15, right? 5 goes into 15 3 times, and 3 times 1 is 3. Now I've got 13/15. the denominators are the same. And so now I can add the numerators. It's going to be the same thing with problems like this. You have to get that common denominator. And so what I like to do is write down 2 fraction bars. Copy the sign in the middle between them. All right. And I'm going to build that least common denominator. The least common denominator has got to be everything in the first denominator and then everything that's different in each denominator that appears after the first one. So I need the x plus 1 and I need the x subtract 1 as my common denominator. So what we're going to do is put this least common denominator into each denominator. Okay, so there's the LCD. There's the LCD again. And I like to copy the original numerator. There's a 3 in the first fraction and a 5 in the second fraction. Now, I like to compare this first fraction with this new and improved first fraction that has that least common denominator in it. And you need to identify what came into the fraction that wasn't there before. So if I look here, this was quantity x plus 1, and now I have a plus 1 minus 1. So the x minus 1 is the binomial that was not in the original denominator. I call that the intruder. So I identify the intruder, and if the intruder comes into the denominator, we also move the intruder up to the numerator. In the second fraction, when I'm comparing this 5 divided by quantity x minus 1 to this new fraction with that common denominator, I'm like, oh, x plus 1 is the intruder. So if it intrudes in the denominator, it also has to intrude in the numerator. Okay? The rest now, really, all I have to do is write 1 fraction bar with the 1 common denominator. And you're going to distribute. Okay, so you're going to distribute here. 3x subtract 3. You're distributing a positive 5, so it's 5x add 5. We're going to combine like terms. 3x and 5x is 8x. Negative 3 plus 5 is positive 2. We're going to put that over the 1 common denominator. You do not have to multiply this denominator out. In fact, you shouldn't, because you need to list the restrictions. I look and I ask myself, can I factor anything? And I answer myself and say, well, yeah, technically I could take a 2 out of each of those. And so when I do that, I get 2 times quantity 4x plus 1 over x plus 1 times x minus 1. Now, it doesn't help me to simplify, but sometimes it will. So always, always, always make sure that you are looking to factor that. Now, I'm not finished because the restrictions are part of the answer. So I look, and back in the original, x can't be negative 1, x can't be positive 1. It can't be either of those there. Nothing got divided out. So my restrictions are x is not allowed to equal negative 1 or positive 1, or it makes my original expression undefined. So this then is my final answer. Okay, the next example that we have, again, the denominators are different. I've got 4 over x, subtract 3 over x plus 3. And we're going to, once more, build our least common denominator. We need everything in the first denominator that happens to be a monomial, just x. And the second denominator has a different denominator, quantity x plus 3. So my one common denominator here is x times the quantity x plus 3. So I'm going to write 2 fraction bars with the subtraction in between. That was the original problem. I'm going to write the LCD in both denominators. I've got x multiplied with the quantity x plus 3. I'm going to copy what was already in those numerators. And now we identify the intruder. If you don't want to draw an arrow, you could put a little dot or underline it. So x was there. If I compare this new fraction with the original, x was there. Here's my intruder. And then there's my subtraction sign. And then the second fraction, x is the intruder. The intruder also needs to move up to the top level. See, folks, when you do this, what you're really doing is multiplying this fraction here by a 1. X plus 3 over itself, x plus 3 is 1, right? Anything divided by itself is 1. I just need to make my fractions look different. And they need to have that common denominator so that I can add the numerators. All right, so what must I do here? Well, I have to distribute. I get 4x times, 4 times the quantity x plus 3 becomes 4 times x, and then 4 times 3, or 4x plus 12. Remember, this is subtraction, so I have to subtract 3x. Be careful if this is a quantity. We'll talk about that in a bit. You put this over the one common denominator. You must simplify by combining like terms. So I've got a 4x and subtract a 3x is a 1x plus 12. And denominator is x times the quantity x plus 3. That's all I can do with it. X and 12 have no common factors. I can't take a GCF out. X plus 12 is a quantity. Remember, this x is not that x, so you can't divide them out. This is a quantity, x plus 12. The only thing left to do is list what your denominator is not allowed to equal. Here, of course, it can equal 0. When x is by itself, it itself cannot equal 0. And over here, x can't be negative 3. And I'm going to circle my final answer. So those two problems were pretty straightforward. The denominators were prime. You could not factor them. And now we're going to go into finding the least common denominator of rational expressions that the denominators have to be factored first. Okay? So we're going to see that when you're finding that least common denominator, you're going to have to factor each denominator completely. Folks, sometimes you're going to have dots. Sometimes you're going to have trinomials. Sometimes you're going to have sum or difference of cubes. Sometimes you'll have perfect square trinomials. All the different types of factoring we've had, you must factor completely. The next thing is to list the factors of the first denominator, all of those factors. It's not enough just to list one. If the first denominator has 3 factors, you have to list all 3 factors. Then you're going to add or include in that list any factors of the second and third denominators that do not appear in the first list. And then finally, we say form the product of each different factor from the list in step 3. This product is what we call the LCD. So again, form that product of each different factor from the list in step 3. That product is the LCD. So now we'll take it a step further on the next page. Sorry about that. And we're going to actually find the least common denominator of the following 2 expressions. Okay, so we're going to put the next page up for us. It says, find the least common denominator of the following. I have 2 rational expressions. 3 divided by x squared, subtract 6x, add 9. And the second rational expression, 7 divided by x squared minus 9. Now, what you need to do is, follow those directions on that previous note sheet. You have to factor each denominator completely. So what I like to do, to save myself a step and to save myself a little time, I like to factor it right underneath. Okay, and so I'm like, oh, x squared subtract 6x plus 9. Oh, this is a perfect square trinomial. X, 3, x, 3, signs are the same. They're both negative. So I've got x minus 3 times itself, x minus 3. Over here, x squared subtract 9 is the difference of two squares, or you know them as dots. That's going to factor as x plus 3 multiplied with quantity x subtract 3. Right, now I want to form that one common denominator. Okay, and the rule is you need everything in the first denominator. Even if it's repeated, you need them all. And then I compare to the next denominator. Is there an x plus 3 already in the list? No, there's not. So I need it. Look at the next one. Is there an x minus 3 in the list already? And you say, why, yes, there is. And so I don't need it again. So finally, I can then say my least common denominator of these two rational expressions is x subtract 3, and also x plus 3. Okay, so we need all the factors in the first one. And in addition, you need anything that's different in each successive denominator. You might say, what? Well, why? Why do you need both of those if they're repeated? Well, for example, and I'll just work through this pretty quickly. If I wanted to add something like 1 over 25 plus 2 over 15, I need some number, some common denominator that both 25 and 15 will divide into. The only number that is, or the smallest, right, the least common denominator is 75. And here's why. Here's why this breaks down that way. 25 could be written as 5 times 5, and 15 could be written as 5 times 3. Okay, you following? So I need this 5, I need this 5. That 5 is already in there. I need this 3. And so my common denominator here is LCD is 5 times 5 times 3, or 75. Okay, and so that's why if you have two factors that repeat that are the same ones in that first denominator, you need to list them both. Okay, now we're going to take a look at adding and subtracting rational expressions with different denominators. Now, these denominators we are going to have to factor. So they're different than the ones we did before. Those other denominators were prime. We didn't have to factor. We just had to get a common denominator. So what you're going to do first is find the least common denominator. You must factor everything completely. Number 2, we're going to write all of the rational expressions in terms of the LCD. That little phrase, in terms of, really just means we need to physically see that least common denominator in every single fraction. If you recall from geometry, sometimes they asked you to give your answer in terms of pi. You probably see that in pre-calc as well. So if your answer is in terms of pi, that means you actually physically see pi in the answer. For instance, maybe the final answer is 2 pi. If we were rounding our answers, you would on a calculator do 2 times that irrational number pi and then round it. But if we want our answer in terms of pi, You will see pi. If I want to write each expression in terms of the LCD, I need to physically see the LCD in each denominator. Okay, you don't want to skip that step. It's going to be very important that you do that. The next thing is you're going to add or subtract numerators. Okay, and that final result is going to go over that one common denominator. Again, we simplify if it's possible, and you always list the domain restrictions. It's part of your answer. And so example 8a that we're going to do is this one where it says add or subtract. In this case, we are subtracting two fractions that do not have same denominators and that can be factored. All right, so I'm going to cross this out. I'm going to cross this out, and I'm going to factor it right underneath. All right. Two binomials. 6 and 4 multiply to 24 and subtract to 2. So I've got x, 4, x, 6. Signs are different. Larger product. 6x is bigger than 4x gets the minus. Over here, multiplies to 6, adds to 7. Well, that would be 1 and 6. Don't forget about the x's. Signs are the same. They're both negative. My LCD here is x plus 4, x minus 6, x minus 1. X minus 6 is already there. So now we're going to write two fraction bars separated by subtraction. And we're going to write the LCD in both fractions. So plus 4, minus 6, minus 1. Of course, when I say minus 1, I really mean x minus 1. X plus 4, x subtract 6, x subtract 1. I like to copy what was already up in the numerator. I like to identify the intruder. The first denominator had plus 4 minus 6. Here is my intruder. The second denominator had minus 1 minus 6. My intruder is plus 4. Remember, you have to move the intruder up. So we got x minus 1. Here we've got x plus 4. Folks, you have to distribute and distribute here. And a good trick or rule of thumb is when it's subtraction, change it to addition and move the negative right there so that you don't forget to distribute the negative to both. All right, first one, x times x, x to the power 2, x times negative 1, negative x. Negative x times x, negative x squared. Negative x times 4, negative 4x. All over the least common denominator, x plus 4, x subtract 6, x subtract 1. Combine like terms. I have some x squares that are going to sum to 0. Okay, they're a pair of opposites. Negative x subtract 4x is negative 5x over the one common denominator, x plus 4, x minus 6, x minus 1. Don't forget to list your denominator restrictions. X is not allowed to equal negative 4, positive 6, and positive 1. Negative 4, positive 1, positive 6. On the next page, there is one more example. I'm going to put the example up. I want you to copy it. I want you to pause the video, and I want you to try that problem on your own. There is the problem. So pause the video and try this video on your own. So hopefully you paused the video and went through the problem. Compare your answer to mine. Notice how I factored. I built my LCD, wrote each fraction in terms of the LCD, identified the intruder, moved the intruder up, changed my subtraction to addition and moved the negative in, distributed, combined like terms, got my final answer with my restrictions. Have a great day.